Hey guys, welcome back to my channel. And oh boy, I found this really interesting paper right here. So, do you know how the transformer architecture is literally used everywhere, including like language, images, video, and audio? But right now, it's aiming for something new, something that I didn't even think about, right? And it's graph. Right. Yeah. So this paper right here, right? It it suggests the idea that LLMs can be directly used to replace graph neural networks, right? And all graph processing need is just human language, apparently, right? But do you know what? Let's dive right into it, shall we? So, wait, but before that, just let me check my OBS. Yep, it works. That's great. So let's get right into it, shall we? So, oh boy. Okay, right. So obviously, LLMs have emerged over the past few years, and it replaced convolutional neural networks and RNNs. Well, look, brother, I'm not so sure about the convolutional neural networks because that isn't a language model. But anyway, okay, right. So as we all know, images and videos and text, everything has been covered by LLMs, right? At least some part of it has LLMs involved, right? But now, right? Yeah, but now language, right, especially human language, is very expressive, right, in its ability to describe complex structures. So, and of course, there are existing works that incorporate problems into generative language modeling framework, but this is still a pretty new area that needs more work to be done. And and because we have the LLMs, therefore it's really crucial whether or not, right, and have this idea of replacing graph neural networks with LLMs. It is essentially like replacing convolutional neural networks with LLMs. It's it's mind blowing essentially, but yeah, but that's what they essentially did in this paper. So, and they call their approach InstructGLM, which stands for Instruction Fine-Tuned Graph Language Model. Um, yeah, and to say that they have highly scalable prompts, they're using natural language instructions. So basically, what they did right here, right, which is really important, is that they use just natural language to describe the geometric structure of the graph, right? And then they directly use supervised fine tuning on the LLM to make graph prediction tasks, I assume. So so this is what they call generative graph learning, and it's something that I have covered in the previous video, but it's not that in depth. But we shall go through this in a bit soon. Okay, so the method surpasses all. Okay, so the method surpasses all GNN baselines. All GNN baselines on these popular benchmarks, right? And this highlights that LLMs can be used for graph machine learning. And I tell you what, this is really unprecedented, right? So the fact that LLMs, just by using human language, can outperform graph neural networks just by using human language. This is pretty insane. So so let's go through it in more depth, but we shall start off with the conclusion because it's going to contain all the information that we need on a high level. Okay, right. So in the conclusion, let's say this work is the first attempt to represent graph structure using natural language description and performing fine-tuning on GPT models for graph learning tasks. And blah, blah, blah. Okay, it's a new foundation model and it outperforms single model GNNs and graph transformers. Wow, even graph transformers? I bet it outperforms something like a graph-former in this case. Okay. Moreover, benefiting from our highly scalable instruction prompts and unified generative pipeline applicable to multi-modality data, InstructGLM can be readily extended to valuable future works along 4 directions. Number 1, using LLMs to generate improved features like tape, SimTeG, and instruction prompts for InstructGLM. And number 2, enhancing InstructGLM with knowledge distillation and iterative training. Okay, and number 3, deploying InstructGLM on more graph tasks such as Q&A. And number 4, extending InstructGLM to other languages besides natural language under the premise that everything is tokenized. Okay, right. So essentially, their idea, right, for future work is to use something like a multi-modal, something like the Gemini model, essentially, but add in graph processing in there. And I think that's quite doable, right? Since you already proved that the LLMs can be directly used for graph processing after fine-tuning. Okay. So that is that. Yeah. And obviously this is for AGI, right? So yeah. But yeah, that gives me a title idea. So it's about multimodal, right? So it's one step towards true multi-modality. Okay, right. So that is what it essentially is in this case, but it comes with a few limitations that's stated. So the primary limitation of their approach is that the input token limit. I bet it's quite small. Okay, for example, 512, which is definitely very small. And in some cases, Llama allows for 2K tokens. It's still considered to be larger, but it's still kind of restrictive if you're dealing with large graph. Okay, so right. So when dealing with large graph, the instruction prompts that are created will not encompass all higher order neighbors within a single natural language sentence due to sentence length limitation. Okay, right. So basically, right, if you think about it, right, if you can't condense all the information into the given range of tokens that you can feed in, then you essentially miss out on a lot of information right there. So that's something that can be fixed with a long context model, just like Gemini. But yeah. So okay, the simplest solution to this problem would be to construct multiple graph description sentences. Hold on. Right, for each training node, central node to enumerate all possible neighbors at corresponding hop level. Okay, but here's the problem, right? It is very inefficient, right? And it takes up too much space in in the token limit, right? Whereas with something like in GNN, where you just have this message passing mechanism, you are you, you don't really have this kind of issue. I mean, it's it's like yeah, the problem with LLMs, right? Is that to process these like interaction information, you need to uh, have this interaction information as an input, right? As an input, as a set of input tokens for the LLM. Whereas for the GNN, everything is done by using the message passing mechanism, and all the interaction information is already accounted in the model parameters itself. So you don't need an additional set of like input tokens or input nodes to account for the neighbor pair interaction, right? At least that's my guess here. Okay, right. So to say, learning from graph sage, we repeatedly perform random sampling from multi-hop lists of the central node until the center line reaches the limit. Okay, so what they essentially do here is that instead of enumerating every single possible neighbors, how about if we just like select a few of them randomly, right? And that seems to work for them. But then again, you have to remember that this thing leads to information loss, right? So obviously in this paper they are going to say it mitigates that issue, but we all know that there's going to be information loss when you do this kind of sampling, right? Right, right. But GNNs, on the other hand, doesn't really suffer this kind of problem unless you deliberately yeah, unless it's like a really huge graph, right? Then yeah, this kind of random sampling does need to take place, right? But it really depends. So okay, despite our implementation achieving good results, we believe that improved neighbor sampling and selection strategies. Okay, so here's their future work. Selection strategies and neighboring sampling protocols can help the model to achieve better prediction quality. And that's understandable, right? So, all right. So how about if we just jump into the meat of the paper here? Obviously, right, there's going to be some intro, but I would assume that you and I both already know a bunch of this introduction stuff, right? So basically it's talking about how like you used to have like these like specialized architectures for different tasks, and now everything is kind of like converging into just using LLMs even for images, text, audios, videos, and now graphs. Everything is converging into a single architecture, essentially. So, right, and to say, okay, however, in graph machine learning, there's a lot more questions that needs to be answered. For example, right? Okay, so typically how you use LLMs for graph processing is number one, you combine LLMs and GNNs where the LLM acts as a feature extractor or data augmentation model to enhance the GNN. So basically what you do is that you give the LLM the graph topology information plus inside a prompt, and then you feed the entire prompt into the LLM, and then the LLM produces a generated rationale or its thought process information, whatever it is, which you can then feed it into the GNN to produce a more accurate response. Yeah, that's a really common approach that you can already find in a lot of papers. Um, okay, but obviously this requires us to train a lot of models, and it's quite annoying, right? And it's expensive. Mhm. So yeah, and another thing that they point out is that just the use of GNNs in this case right? You actually limit the prediction accuracy in some way because GNNs and its message passing mechanism is well known for its problem called over smoothing, where over iterations of neighboring interaction, all nodes essentially converge into the same representation information, which absolutely destroys the prediction accuracy of the entire thing. So that's something that we want to avoid. And okay, and point two, purely relying on transformers, but necessitating novel designs of embeddings for nodes and edges, right? So another branch of effort in the community is to try to use the transformer architecture, but they propose some kind of like new designs for the token embeddings for the nodes and the edges, or they create like a complicated graph attention modules to capture the structure of the graph. This type of approach, obviously, it is costly. You know, you're performing the attention mechanism for every single one of them, and it's like really expensive and slow. And right here it says that it limits each node's scope to only one hop neighbors, which obviously, right, we need more than one hop. Okay. Additionally, the complex pipeline with special attention mechanisms prevents the model from directly observing and learning the structural information like GNNs, which restricts their improvement on performance. So, in this work, they propose InstructGLM. All right, and the question is, right, can LLMs replace GNNs like it did with convolutional neural network and recurrent neural networks? Can it defeat GNNs, right? Obviously, the answer is yes from the paper, but let us see what they have to say about the advantages of using their approach in general. Flexibility, okay. A, a natural language sentence is effectively capturing the connection at any desired hop level and intermediate paths without iterative message passing and aggregation. Okay, so it's saying that it is able to do that without any sort of like iteration. I don't see how that's a selling point in this case. I mean, I get that a sentence can describe that, but in order to get to that point, right, how, yeah, yeah. I mean, I don't necessarily agree with this. I mean, I kind of understand what they're saying. I mean, you can describe the interaction, but the problem would be how do you get to that description, right? But yeah, but anyway, right? Okay, even multimodal features of node and edges can be directly integrated into natural language prompts, making natural language a flexible medium for graphs. And secondly, scalability. Injecting graph structure into multiple language sentences enables mini batch training and uh, gradient independent gradient propagation, which facilitates scalable training. Okay, now with GNNs, right? GNNs can be trained in batch-wise. Right, it can be trained in batch-wise, but the LLMs can also do the same. So I don't see I don't see how it's like um, I don't see how this is a selling point in that case. But you could argue that, oh yeah, we could scale up the LLMs in terms of the number of layers, which is something that we cannot do with graph neural network layers, right? Yeah, but they didn't say that in this case, so I would have to not really agree on that. How about compatibility? So with structured descriptions, InstructGLM is able to consistently reformulate various graph learning pipelines. Okay, right. Okay, so it's saying that it's compatible with a lot of different domains. Fair enough. Okay, so in this paper, they focus on node classification and link prediction. Okay, so right. So that's that, and there's a whole bunch of details here, but I think they're kind of redundant for our case. All right, so how about this? How about we get right into it, shall we? So we're gonna skip related words because those are not that interesting. And now into the meat of the paper. So we introduced InstructGLM, a framework utilizing natural language to describe the graph topology and the features of the node and edge for the LLMs. All right, and now starting off with a graph. Okay, so a graph can be defined as this statement right here, this mathematical tuple right here, right? So nodes, adjacency matrix, the edge set, the edges, right? And then you have the node feature and the edge feature in this case. So obviously, if you think about it, right, a graph can literally represent anything, right? It can represent an image, the interaction between each pixels of the images, or it could represent the words in the sentence and the connection between them, more like the correlation between them. Yeah. So okay, and here's their prompt design here. So the prompt here is number one, what is the largest hop level of neighbor information about the central node in the prompt? Okay, right. So they have to consider like a few things when designing the prompts. So first of all is what's the largest neighborhood, right? Neighborhood information around the center atom that you need to take account in the prompt. And secondly, does the prompt need to include node features and edge features? And number three, for prompts with larger or equal to two hop level neighbors, right around the center atom, does the prompt need to possess the information about the intermediate nodes or the paths leading to the neighbor nodes? Does it require this kind of like intricate details, right? So okay, let's see. Sorry about that. Just go through a bit. Okay, okay. So about question one, the hop level. All right. Okay. They say prompts can be classified into two types: those exclusively containing one hop information and those with a maximum of 2 to 3 hop connection details. And previous work. Okay, just give me a second. Right here. Okay, sorry, I'm back now. Okay, right. Yeah, and previous studies have shown that if you use up to 3 hop of connectivity, it's already enough because anything beyond 3 hops is not going to have a major impact on the accuracy of the model, right? Sometimes it can be detrimental as well. Yeah. So therefore, the maximum level of neighbor information included in the prompt is up to 3. Okay, let me tell you something right here. So I would assume that these findings about the number of hops, right, and and how many level hops you need in order to get the best accuracy, well, it actually depends. In my case, right, I found out that if you don't include like the highest number of hops in like chemistry tasks, it usually is really bad, right? So in my case, I have to include everything, right? But for something like archive graph topology, it might not be necessary at all. Well, so okay, benefiting from the flexibility of natural language, our prompts can accommodate structural information of any hop level. Obviously, if you have enough GPU power, then maybe. Okay, regarding question 2 and 3, there are two possible scenarios. For example, if or not to include the node or edge features in the prompt, and if or not to include the intermediate connecting paths in the prompt. Okay, the denote an instruction prompt as T dot, such that I equals to T dot, T the input, right here. So you basically take the entire graph and feed it as an input to incorporate it into the instruction prompt. And this will be the natural language sentence to be fed into the LLM. And V is the central node of the prompt. Okay, so yeah, and I go through a whole bunch of like examples here. Right, for example, if you have like at most 2 hops worth of information, so it will be represented by this, right? So, or the more complicated notation would be here, right? So, but that's not the most important details for our video today. So, okay, right. So what do I have now? Okay, so section 3.3, generative instruction tuning for node classification. In node, okay, right. In prompt engineering or in context learning, pre-trained models are usually frozen instruction tuning. Okay, right. Okay, so they directly convey the requirements of the downstream tasks by fusing the original input data with task-specific instruction prompts under the framework of multi-prompt training, right? So this can be effective, especially with supervised fine-tuning, and you couple it with reinforcement learning from human feedback, obviously, right? So, and I think that's what they're going to be doing. So, okay, and now finally we get to talk about InstructGLM. So, and I describe it as a multi-prompt instruction tuning framework for graph learning. So, what it essentially do right here, if we go through this quickly, it is essentially using a LLM, right? Whether it be a decoder, encoder decoder model like the original transformer architecture, or you just use the GPT architecture, right, as the backbone. And then what they do is that they combine all their instruction prompts, right? So which includes the different hop levels, the different the diverse structural information as an input for the LLM, right? So okay, and the same by using language, they can describe that. Makes sense. Okay, so something worth noting is that they concentrate on solving node classification in this task. They train InstructGLM to strictly generate the category label in natural language, and okay, and they use NLL, right? So negative likelihood loss as their objective function here. So okay, and this is the loss function, the NLL loss function there. And the prompt is something like this. Classify the central node into the following categories, right? Blah, blah, blah. Pay attention to the multi-hop link relationships between the nodes. And the question would be, which category should the node be classified as? Yeah. So that's the problem that I fed in there. Okay, and I also describe about like what prior works inspired their approach, but that's not gonna be relevant for our case right now. Okay, so let's skip that. Okay, all right, here. Section 3.4, auxiliary self-supervised link prediction. All right, so okay, so they introduce a self-supervised link prediction as a foundational auxiliary model for InstructGLM. So given any hop level and central node, the first randomly select a neighbor or non-neighbor at this hop level as the candidate. Right. So if we draw it, it would be something like this. So if you have a central node right here, let's say something like that. Right. Let's say this is your central node, and you randomly select some other nodes. Then you instruct their model to discriminate whether there is a connection between the central node and the selected node. So it's like, okay, if I select this one, is it connected? Yes or no, right? So obviously we want it to predict that, yeah, there is a connection, right? So that's their auxiliary task, right? And this is called a link prediction. So right here, okay, and the problem is perform link prediction for the central node. Pay attention to the multi-hop link relationships between the nodes, okay? And the generative question part is which other node will be connected to node within some H hop level, and the descriptive part would be will this node be connected to this node within some level of hop. Okay, so I don't know if they wrote down the loss function here, but I think that's pretty self-explanatory either way. So okay, and now we have reached the section point right here. So let's go through the figures then. Okay, so the figures are okay, right. So let's go through this one, table one. So okay, obviously this result is on ogbn-arxiv. They report the accuracy of graph neural networks, which is at the top. Um, okay, right. The accuracy of GNNs at the top, and the graph transformers at the middle, and their model, their language model at the bottom. So let's see. So okay, so you can see the GNNs are pretty much like around 50% to 74%, and the graph transformers are within about the same range. But as soon as we get to language models here, well, as you can see, if we use like a T5 base model, it seems to be around the range as as the GNNs and the graph transformers, which is insane, right? Because I would expect these to like perform worse, but apparently it does work, right? And when we take a look at and when we okay, and here's the important part, right? As we go down here, right, it is essentially increasing the number of parameters, right? Increasing the number of layers, and they have shown that when you increase the number of layers, right, the performance improves as well. And I think that's the major selling point of this work, right? Is that you can improve, right? So what this tells us is that they can improve the accuracy of graph tasks, right? Without, right? without worrying about about over smoothing due to the fact that we are using LLMs, right? When we are using language modeling, right? Um, then we don't have to worry about that, and not GNN, right? So I think this is a pretty revolutionary insight here, is that we don't even have to worry about over smoothing at all, right? Which is pretty good. So let's take a look at more results, right? So let's see, Cora and PubMed, right? Table 2, Cora and PubMed. And the results also speak for themselves, right? But in this case, the Llama 7B model seems to be performing a bit worse compared to the other models. Interesting. But regardless though, I think it's pretty good. Oh yeah, but one thing is to be sure, right? Is that if you compare the models, right, under the same number of parameters, you will actually find out that these LLM models will eventually underperform compared to GNN models under the same number of parameters, especially in the lower number of parameter range, around like a few 100,000 para parameters to a few million, right? Obviously, if we scale it up to like 7 billion, right? Obviously, the language models is gonna outperform the GNNs due to the fact that the GNNs will be over smoothing in that range of number of parameters. So yeah, okay, right. And you use lowering adaptation for the fine-tuning process. Right, okay. And now table 3. This is about their okay, so this is about so this is an ablation study. So obviously, right, they have okay, so if we take a look at these two, the first two rows, right? They essentially show that if you include the link prediction of auxiliary tasks, the accuracy improves by a bit for archive, but it improves quite a lot uh, for Cora, and it improves a bit for PubMed. Mm, all right, but yeah, so yeah, yeah, so obviously all of these components, as they have shown here, are pretty essential for their approach to it would work, right? So so right now, yeah. Yeah, I think that's about it, really. So okay, right. So what have we learned from this paper? Well, essentially, right, they use two different loss functions, one for node classification and the other one for a link prediction. And the link prediction is kind of like a trick to further boost the accuracy, but whether or not it's effective is solely dependent on the task. Like it works really well for one, but it kind of increases the accuracy of some other tasks just by a few 0.1% or something like that, in that sort of range. So yeah, everything is going to be taken over by the transformer architecture, and now it's like language describing the graph. I mean, if you can describe the graph, then you can basically use language for anything, really. Describing a video frame by frame, just using language. That's pretty insane. Anyway, if you like what you saw, please like and subscribe. Comment down below if you have anything to say, and I will catch you all in the next one.